video, we're going to learn about Mohr's moment area method to determining slope and deflection. Now, Mohr's moment area method works different compared to Macaulay and integration. It almost works like superposition. Let's look at the steps that you need to follow. Now, step 1 says separate the beams according to the loads, and then for each new beam, calculate the reactions and do shear force and bending moment. So assume you're given a beam, a simply supported beam. And you have a point load somewhere here, and another point load somewhere here, as well as a UDL somewhere here. So with Mohr's moment, you're going to separate the beam. We're going to create new beams according to the loads that are applied on the original beam. We're going to have a beam for the point loads and a beam for the UDLs. And then for each beam, you're going to calculate the reactions. And then after the reactions, you're going to do your shear force and bending moment diagrams for each beam. Now let's look at step 3. Step 3 says choose your reference point R, according to the boundary conditions where you know slope is 0 or deflection is 0. Now, this is a symmetrical beam, assuming it's a symmetrical beam. And we know that at the center, at midspan, our slope is 0 and our deflection is max. At the supports, we know our slope is max and deflection is 0 for both supports. So for your reference point, let's assume, let's say, calculate the slope at A. Let's say this is A, B, C, D, E, and F. Let's say they're looking for slope or deflection at point A. You're going to say, okay, for this point, you're going to say the slope at A, referencing, you can reference either points where you know something for sure. We know our deflection at F is 0. And we know our deflection at C prime, which is the turning point, or D prime, or you can call it G. You know our deflection, our slope at G is 0. So you can use either conditions to find your slope and deflection. Now the slope equation is basically going to be your slope at the required point, according to our reference, will be the sum of the bending moment areas divided by AI. And then the deflection equation is going to be your point that they're looking for based on our reference. It's going to be the sum of the bending moment areas times the centroid to that point, from our reference to that point, or from our shape to that point, divided by EI. And then now, if you're given our I-axis, our moment of inertia not being constant, you'll have to modify your bending moment diagrams for each diagram. I'm gonna modify the bending moment for your point loads and the bending moment for your UDLs. Then after modifying, by modifying, basically, you're going to say the bending moment divided by AI, and then 10 to the 3 to convert the units. And then after modifying our slope, P reference point will basically be equals to the bending moment area. And then our deflection is going to be P R, the sum of bending moment area times our centroid. And then for a built-in beam, for a built-in symmetrical beam, you will have a bending moment diagram for the moments at the support, for the moments that they built in. Let's assume we have a beam like this with a UTL and say 2-point loads. Then you'll have an equation, you'll have a beam for the point loads, a beam for the UTL, and a beam for the walls. And then for each of these beams, you'll have your shear force and bending moment. And then we'll focus on the bending moment diagrams to find force, slope, and deflection. But to find the moment, to find these moments, because they'll be unknown, to find these moments at the walls, you will split the beam at the center and equate the bending moment areas to 0. You'll split the beams like so, and then you'll equate sum of bending moment areas, sum of uh, bending moment areas is equals to 0. And these moments right here, they will be negative, meaning the bending moment diagram for this one, so this is 0, this is 0. It will go down to negative and negative. There will be negative m here and a negative m here. So we're going to have the bending moment for the point loads plus the bending moment for the UDLs minus the bending moment for the wall, which will give you 0. Now let's look at, before we do an example, let's look at our shapes one more time, because we will need them in this method. We'll be using our areas and our shapes and our centroid of our shapes. And we know for a triangle, our area is half base times height, and then our centroid, call this base, is 1/3 and 2/3 times b. And then we'll have a shape like this. We know our area is 1/3 base times height, and our centroid will be 1/4 base and 3/4 base. And then we'll have a shape that's like this, a quarter circle. The area is 2 divided by 3 base times height, and then the centroids, this side it's 3/8 base and 5/8 base. So we'll be using these shapes, especially these two. Yeah, especially these two for the UTLs. These ones are from the UTLs. This one is from the point loads. And then our rectangle is from the moment. B times height, base times height. It's our area. And then our centroid is B over 2 and B over 2. Now let's look at a simple example of a cantilever. Let's say we're given a beam, cantilever beam. And then our E is 200 GPa. And our I is 100 10 to negative 6 meter 4. Let's say we're looking for slope at C and deflection at A. So we'll have our A, B, C, D, and E. So the first thing we'll do is we'll separate our beams. Let me zoom out a little bit. Let's choose a glue. So we'll have the beam where it's simply supported, which will have a reaction as well as a moment of R, E, and ME. Let me change the direction for a moment. It's going then we'll have our point load of 30 kilonewton. And then we'll have our shear force diagram, which will be here, and our moment diagram, which will be here. So 0, 0, 0. Okay. For our RA, to find our RA, we'll use sum of forces up as positive is equals to 0. And then we'll have minus 30 plus RA with 0. Our RA is 30 kilonewton. And then for our moment, we'll use sum of moments clockwise positive is equals to 0. We'll have ME minus 30 times 2, sum of moments at E is equals to 0. Then we'll have our ME minus 30 times 2. Our ME is 60 kilonewton meter. Now let's calculate our shear force and our bending moment. Let's draw a line, separate our page. Okay, we know the shear force. The shear force from A to D, our A to D left is 0. Then D right is minus 30. E left is minus 30. E right is minus 30 plus 30, which is 0. And then let's do our bending moment. Also, we know from A to D is 0. And then our E is 30 times 2, which is 60 kilonewton meter. And then that's E left, and then our E right will be 60. Sorry, it's minus 60. Will be minus 60 plus 60, which is equals to 0. Now let's draw our diagrams. So we have 0 here, 0 there, 0 there, and 0 here. And then we go to minus 30. And minus 30. And then our bending moment diagram, let's use red. We'll have 0 there, 0 there, 0, and 0. And then our E will be here at minus 60, and then back to 0. Now let's look at the diagrams for our UDL. Okay, we have our UDL at this point, which is 5 kilonewtons per meter. Then we'll have our reaction, as well as our moment, which will go anti-clockwise. Clockwise, I mean. And then our reaction will have sum of forces. Up is positive. We have minus 5 times 2 plus RA, which is equals to 0. RA 10 kilonewton. and then sum of moments at A clockwise positive is equals to 0. And then we'll have our MA minus 5 times 2 plus 4 is equals to 0. It says 5 times 2, 2 over 2 plus 4. And then our MA will be and then our MA will be 50 kilonewton meter. Then let's draw our diagrams. Our shear force diagram and our moment diagram. 0, 0. Then our shear force diagram. From A to B. Okay. Our A is 0. Our B is 0. Our C is minus 5 times 2, which is minus 10. D is minus 10. Our D is here. Then our A left is minus 10. And then our A right is minus 10 plus 10, which is 0. Let's draw our shape. Let me see. We have A 0, B 0, A B, and then our C left is minus 10, which is here. So it's basically going to move from here to somewhere around here, and then it's going to go straight back to 0. Minus 10, minus 10, minus 10. Now let's do our bending moment calculations. Our A is 0, B is 0. And then our C will be minus 1 over 2 times 2 times 10, which is 10. 0.5 times 2 times 10, which is minus 10. And then our D will be minus 10 times 2, which will be 30, should be 30, minus 30. And then our E will be minus 30 minus 10 times 2, which is 50, minus 50. That's A left. And then our A right will be minus 50 plus this 50, which is back to 0. Okay, and then we have our 0 here. Then B to C with minus 10 at C, and this is UTL, so it's going to curve something like that, and then with 30 at D and 50 at E, something like this, and then back to 0, minus 50, minus 30, minus 10. Let me draw it this time, minus 10. Now these are our bending moment diagrams. We have the first one for the shear force, which is here, PM1, and for the EDL, PM2. Let's see how many shapes we'll have since we're using areas. Let's use loose fine. This is our first shape, which is shape 1. Then we come here, we have the inverted half of a circle, which will be our shape 2. And then we break this one here. We have our shape 3 and our shape 4. So we have 2 meter, 2 meter, 2 meter, 2 meter. That's A, B, C, D, and E. Now let's look at the question, what they're looking for. We are asked to find our slope at C as well as our deflection at A. Let's start with our slope now. Remember, when you're looking for a reference point, you need to know a certain boundary. You need to know a certain point, so you can use it as your reference. Let's redraw our diagram. It's fine, let me not put the lines now. So we had a cantilever beam. We had a point load. Okay, we had a UDL here. And we had a point load here. We know our beam is going to bend downwards. We know here our slope is max and our deflection is max. And we know at the wall our deflection is 0 and our slope is 0. So we'll use this point as our reference. That's our point R. Now our slope equation, our slope at C referencing B, AB, we know our C is here. So for our slope, we're going to use shape 3, 4 as well as shape 1. Our slope is going to be the sum of our bending moments areas divided by EI, which is the sum of A1 plus A2, plus A3 plus A4 divided by EI. Let's bring it over here. Our A1 is it's a triangle and we have 60. So you have minus 1 over 2 times 2 times 60 plus our A3 is a rectangle, which is 2 times our height right here will be 50 minus, okay, our height here is 10. Yeah. So we're going to have plus our A4, our A3 Let's say this is A31 and that's 32. Where's our C? Oh yeah, no, it's fine. Our A3 is the full rectangle, so it's going to be 4 times 10 plus, which is minus 1 over 2, 4 times 50 minus 10, which is 14. Everything divided by AI. Then we have minus 180 divided by AI, which is minus 180 divided by 210 to the negative 9, then 160 and 10 to the negative 6. Now, there's different ways to write this equation right here. 10 to the 3. You can write it like so. 180 divided by 200 times 10 to the 6. 160 times 10 to the minus 6. Or 180 200 times 160. Then you get 5.625 times 10 to the negative times 10 to the negative 3 radians. Now let's look at our deflection. First, let me explain this part. In this part, these 3 cancels out one of the 3 here, and then we're left with 6. And then in this part, this 6 cancels out the negative 6, and then we're just left with this equation. All of these equations will give you the same answer. But the dangerous thing about it is not knowing your conversions. If you don't know conversions, then it's risky to use one of these 2. Now let's look at our deflection. Okay, let's do it on the side. So our deflection is at A, and in reference to E, since we know something at E, which is sum of the bending moment areas times centroid divided by EI. So what we'll have here is more space. We'll have our deflection at A, reference to A, which is A1 plus A2. Since our A is at the end, we'll use all of the areas, plus A3 plus A4 times the centroids x, 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 and x divided by EI. Our A1 is our triangle, so we're going to have minus 1 over 2 times 2 times 60 times our centroid. And we know that if we split the triangle, we know that if we split our triangle in the center, this side will have 1 over 3 and 2 over 3. Since our point is at A, we'll use 2 over 3 as our centroid plus the remaining distances towards A. Then for our shape 2, we know our centroid is 3 over 4 this side and 1 over 4 this side. So we'll be using the 3 over 4 side for our calculations since it's on the side of our point. Now let's go back to our calculations. Then our reference will be, our centroid will be 2 over 3 times our base, and then plus the remaining distance going towards A. So we have 2 over 3 times 2 plus 2, 4, 6. Plus our second area, which is 1 over 3. Our base is 2. Our height is 10. That's negative. And then we said it's 3 over 4 times base plus the remaining distance. I think it's 4. Let's check. 3 over 4 times base and then plus 2. My bad. That's plus 2. And then plus our shape 3, which is our rectangle. Shape 3 is our rectangle. We have minus 2 times 10. Shape 3, no, it's not 2, it's 4. 4 times 10 times our centroid, which is 4 over 2 plus 4. And then plus our shape 3, which is minus 1 over 2. 4 times say it's 40. And then our centroid is also gonna be 2 over 3. Our base is 4. Plus the remaining distance, which is also 4. Therefore, the deflection at A, referencing A, will be minus 1 over 2 times 2 times 60 over 3 times 2 plus 6. Our area 1 will be minus 440. Our area 2 70 over 3. Our area 4 is 240. Then our area 5 all of this divided by Pi, which is 440 plus 70 divided by 3 plus 240 plus 1600 divided by 3 minus 1, 2, 36.667 divided by 200 times 160, which is negative 0.0386 meters, and which is negative 88.646 millimeters. That's how we use Mohr's moment error method to determine our slope and our deflection. In the next video, we will look at a built-in beam as well as simply supported beams.